AI doesn't run on code. It runs on electricity. And right now, the world doesn't have enough of it, not for what's coming. Every major technology company on Earth is racing to build the most powerful AI systems in history. They're spending hundreds of billions of dollars on chips, on data centers, on infrastructure, and they're all hitting the same wall. Not algorithms, not silicon, not talent, power. A single AI data center today consumes between 100 and 300 megawatts of electricity. That's the equivalent of powering a city of 100,000 people, from one building, on one piece of land. Now consider what is being planned. Microsoft, Google, Amazon, Meta, and Oracle have collectively announced AI infrastructure investment exceeding $1 trillion over the next several years. Analysts estimate that capital could translate into 500 to 800 new hyperscale facilities globally before the end of the decade. At an average of 200 megawatts per facility, that is 100 to 160 gigawatts of new electricity demand. To put that in perspective, 160 gigawatts of continuous demand would rival the total electricity consumption of multiple mid-sized European economies. Countries with tens of millions of citizens, industrial bases, transportation networks, and heating systems. All of it, matched or surpassed by a single industry. In less than a decade, the United States currently operates at roughly 400 gigawatts at peak demand. AI infrastructure alone could add between 20 and 40% to that figure before 2030. Not gradually, not predictably. In concentrated bursts, in specific locations on timelines that no utility planned for. The grid was not designed for this. And the problem is not just the scale, it is the speed. AI scales in quarters. Infrastructure scales in decades. That gap is not a policy failure. It is a physical reality. And it is the defining constraint of the AI economy. To understand why this gap is so consequential, you need to understand how different AI demand is from anything electricity grids were built to serve. Traditional industrial demand follows rhythms. Factories slow at night. Offices empty on weekends. Residential consumption peaks predictably in the morning and evening. Grid operators have spent a century modeling these patterns. They plan generation capacity around them. They size transmission infrastructure to match them. AI breaks every one of those assumptions. A hyperscale training cluster has no off-cycle, no peak hour, no weekend. It runs at full capacity continuously, for weeks, for months. Consider the arithmetic. 100 data centers at 200 megawatts each. That is 20 gigawatts of constant uninterrupted demand. 20 gigawatts is the equivalent of approximately 20 large nuclear reactors running simultaneously at full output. It is more than the entire annual electricity consumption of countries like Ireland, New Zealand, or Portugal. Generated not by a national grid serving millions of citizens across thousands of square miles, but by a single industry, concentrated in specific corridors, arriving faster than any infrastructure system was designed to absorb. And that is before accounting for the other forces compressing the same grid simultaneously. Electric vehicles, industrial electrification, manufacturing reshoring driven by the CHIPS Act and the Inflation Reduction Act, cloud computing infrastructure that predates AI entirely. Model the cumulative pressure. AI adds an estimated 30 to 50 gigawatts of new demand in the United States alone by 2030. Electric vehicle adoption adds another 30 to 40 gigawatts over the same period. Industrial electrification and manufacturing reshoring add 15 to 25 gigawatts. Combined, the United States grid could face 80 to 100 gigawatts of new demand by the end of the decade. On a system where transmission expansion has been marginal relative to the scale of new demand now being projected, the infrastructure did not keep pace before AI. AI has made the gap structural. The last time the United States rebuilt its energy infrastructure at this scale was during rural electrification and post-war industrial expansion. That took decades of coordinated federal investment, regulatory reform and industrial mobilization. What is being asked of the grid today is comparable in magnitude, and the timeline being demanded is far shorter. The grid is already showing what happens when industrial demand outpaces infrastructure capacity. In Northern Virginia, the data center capital of the world, Dominion Energy has been forced to pause new grid connections at multiple substations. Transmission capacity is exhausted. Companies with approved projects, secured land and delivered hardware are waiting for grid connections that cannot be provided. Not for months, for years. In Ireland, the grid operator EirGrid imposed a moratorium on new data center connections in Greater Dublin after projecting that data centers would account for over 30% of national electricity consumption by 2030. The country could not build generation fast enough to match what one industry was demanding. In Georgia, utility planners revised their 20-year demand forecasts upward by double digits within a single planning cycle. The revision was driven almost entirely by data center announcements. These are not hypothetical scenarios. They are documented supply failures happening now in some of the most developed electricity markets in the world. But there is a deeper structural problem that these visible constraints only partially reveal: interconnection queues. In the United States, there are currently over 2,000 gigawatts of generation capacity sitting in queues waiting for approval to connect to the grid. That figure represents total capacity requested across all ISO and RTO interconnection processes: solar, wind, storage, gas and nuclear combined. Not all of it will be built. Many applications are speculative. A significant portion requires costly transmission upgrades before connection is feasible. But even if only a fraction materializes, the scale of congestion reveals structural friction that capital alone cannot resolve. The system was not designed to process this volume of requests, and it is not processing them quickly. Building new high-voltage transmission lines takes 10 to 15 years from planning to operation. Permitting involves federal agencies, state regulators, county governments, environmental review processes, and individual landowner negotiations. Any one of these can introduce years of delay independently. A project can be fully funded, fully engineered and federally approved and still spend 5 years navigating state and local opposition. This is the antagonist nobody names directly. Not a competitor. Not a technology limitation. A regulatory architecture designed for deliberation. Operating at deliberation speed. In an era that requires something closer to wartime industrial mobilization. Go deeper into the supply chain and the constraints multiply. Large power transformers. These are the devices at the heart of every substation. The equipment that steps electricity between voltage levels and makes grid power usable at the point of consumption. They are not manufactured in volume. They are not available off the shelf. Each one is custom engineered for a specific application. The largest weigh 400 tons. They are assembled over months by a small number of specialized manufacturers operating at or near capacity. Lead times that were once 12 to 18 months have stretched to 2 and 3 years. Manufacturers supplying components to GE Vernova, Siemens Energy and ABB are running backlogs that extend into the second half of the decade. A technology company can secure land, obtain permits, order servers, hire 1,000 engineers and still watch its entire timeline extend by years because the transformer required to connect its facility to the grid has not yet been manufactured. Capital does not solve this. Industrial capacity solves this. And industrial capacity takes years to build. AI scales in quarters. Infrastructure scales in decades. Now layer on the generation problem. More power is not enough. AI infrastructure requires stable power, reliable baseload generation that delivers consistent output regardless of weather, season or time of day. Solar does not generate at night. Wind does not generate when air is still. A training cluster running at 3 in the morning during a windless winter night cannot pause. The hardware runs. The demand is constant. This operational reality is driving technology companies toward energy sources the sector had largely moved away from. Constellation Energy, the largest nuclear operator in the United States, has signed a long-term power agreement with Microsoft that includes support for restarting 3 Mile Island, a decommissioned plant brought back specifically to supply AI infrastructure with continuous carbon-free baseload power. Google has signed agreements with Kairos Power for small modular reactor deployment. Amazon has made direct investments in nuclear development projects across multiple jurisdictions. These are not symbolic clean energy commitments. They are procurement decisions driven by a single operational requirement: continuous, reliable, high-density power. A requirement that nuclear satisfies and that most other generation technologies cannot match at scale. But utilities move at utility speed. Regulated, methodical, subject to rate cases, regulatory approvals, and capital allocation cycles measured in years. AI scales in quarters. Infrastructure scales in decades. Now consider what closing that gap actually requires in concrete terms. The United States needs to absorb an estimated 80 to 100 gigawatts of new demand by 2030. Replacing that with nuclear generation alone at roughly 1 gigawatt per large reactor would require constructing between 80 and 100 new units. The United States hasn't built nuclear capacity at that pace in modern history. Under current regulatory frameworks, each plant takes 15 to 20 years to permit, build, and commission. Replacing it with large combined cycle gas plants, each capable of 500 to 700 megawatts, would require building approximately 140 to 200 new facilities. The capital required across generation, transmission, substations, and interconnection runs into the multiple trillions of dollars. Over a timeline the market has not yet fully priced. This is not incremental grid maintenance. It is the largest energy infrastructure reconstruction the United States has faced in generations. And it is being driven not by population growth or industrial policy, but by the electricity demands of artificial intelligence. Now look at where this is already reshaping global power. Not technological power, geopolitical power. The geography of AI development is being redrawn along energy lines. The regions winning the AI infrastructure race are not the ones with the most engineers. They are the ones with the most reliable megawatts. The Pacific Northwest attracts hyperscale investment because legacy hydroelectric infrastructure provides abundant, low-cost, carbon-free baseload generation. Scandinavia attracts inference infrastructure because cold climate reduces cooling costs, hydropower provides continuous clean generation, and permitting environments are more rational than most of Western Europe. The American Southeast is absorbing massive data center investment because utilities like Duke Energy and Dominion are moving aggressively on grid expansion, and because existing industrial transmission capacity provides a foundation newer markets lack. And then there is the Middle East. Saudi Arabia, the UAE, and Qatar are deploying sovereign wealth at scale into AI infrastructure, not because they have the deepest talent pools, not because they have the most favorable regulatory environments, because they have an asymmetric advantage that no amount of software investment can replicate. Energy, abundant, cheap, available at any scale the industry demands. The Gulf states understand that energy surplus, once treated as a liability during the energy transition, has become a strategic asset in the AI era. They are converting hydrocarbon infrastructure into compute infrastructure. And they are moving at a speed that permitting constrained Western democracies cannot easily match. This is the equation that is quietly restructuring global power. AI equals compute. Compute equals electricity. Electricity equals sovereignty, and sovereignty, in the AI era, is measured in megawatts. The nations and regions that can guarantee stable, abundant, affordable power to AI investors will attract the compute capacity that defines intelligence capability. The ones that cannot will find themselves dependent on infrastructure located elsewhere, running models trained on hardware they do not own, in data centers they do not control, in jurisdictions whose strategic interests may not align with their own. This is the pattern that played out in semiconductor manufacturing. The countries that invested in fabrication infrastructure in the 1980s and 1990s built structural advantages that cannot be replicated quickly regardless of how much capital is now deployed. Taiwan's position in chip manufacturing took 40 years to build. It cannot be unwound in 5. Energy infrastructure operates on the same logic and the same timescales. The decisions being made today, about generation capacity, transmission investment, transformer manufacturing, nuclear restart, interconnection reform and grid modernization, will determine where artificial intelligence scales over the next decade. Not decisions about model architecture. Not decisions about software frameworks. Decisions about megawatts. The companies that understand this earliest are already positioning. NextEra, Constellation, Duke, GE Vernova, Siemens Energy. Utilities and industrial energy providers that spent a century as regulated commodity businesses are becoming strategic infrastructure, load-bearing elements of the AI economy, with pricing power, long-term contracts and structural relevance that the technology sector is only beginning to fully price in. The regions that move fastest on permitting reform, generation investment and grid modernization will not just attract data centers. They will attract the training infrastructure that defines the frontier of AI capability. The inference capacity that powers the applications billions of people use every day. The compute density that determines economic and strategic advantage for the next generation. Adding 100 gigawatts in under a decade would require building generation capacity at a pace not seen in modern American history. This is not a software problem. It's not a semiconductor problem. It's a physical infrastructure problem. And physical infrastructure moves slowly. The outcome of the AI race will not be decided in a laboratory. It will not be decided in a data center. It will be decided in substations, in transmission corridors, in energy policy decisions made today whose consequences will compound for the next 30 years. AI scales in quarters. Infrastructure scales in decades. And the clock is already running.